Hi. Last lecture we discussed the placement policies for the cache, and what we said basically that the CPU, when it issues the address for accessing the memory to the cache, um, this address really can be partitioned into three fields: the the tag, the index, and the block offset. We'd like to refer to the index and the tag as the block address. Okay. So, for instance, if we have a what the index does, it points. If we look at this cache here, if we zoom into this cache and look at it in more details, this cache consists of several sets. Okay, set 0 all the way to the end, and this index points to the set. Now, in the direct mapping, every set of those has one block. In the fully associative, the entire cache is one set, and that's why we don't have this index field in the fully associative. In the K-way, the set includes K blocks. So there a choice where the block can go anywhere in these K places. Okay, so let's continue our discussion based on what we have, based on this understanding. Now, we will talk about the tag and the valid bits, and basically that when there is how do we make sure that the data in the cache is the one that the CPU wants. There is first, for every location in the cache, there is a valid bit that is associated with the block. If the valid bit is 1, it means this block is present. If the valid bit is 0, it means the block is not present. How could a block be not present? Well, if you come up out of reset and you power up your system or you start program fresh, chances are you won't have data in the cache. So you will have those are invalid. So in particular, when you come up from power up, so you have to have a match for the tag, and you have to have the data stored there as has the valid bit equals 1. So here is an example that we will look here, and it should help us understand the concept of the valid bit here. Um, let's take an example of a cache of 8 blocks. Every block is one word. Okay, well, this is uh, too simplistic, but it's okay. So every block is one word. So basically, whatever address I have, we don't have a block offset. The address that I will look at right now has only the tag and the index. Okay, the memory has 32 words, which means the address is 5 bits. That's basically what it means, 5 bits. And okay, and let's see. What kind of direct mapping. Okay, since I have direct mapping and I have 8 blocks in the cache, if we do our previous math, we'll realize that these 3 bits are for index, and the first 2 will be for tag. Again, there is no block offset because the block is so small. Here he assumes one word per block, so we don't have a block offset bits. Okay, so the least significant 3 bits are for the index. So now, if now we will see the dynamics of the cache when addresses are issued to the cache. What happens to the cache? The very first address here, we issue an address 22. And if we decode this in binary, we'll see this is 10110. Now, we go to 110. This is to this set, and it was before there was nothing, so that caused a miss, right? So since a miss, meaning the data is not in the cache. Why the data is not in the cache? Because if you look at the previous slide, there is no data here. Valid n means no data. So this caused a mess. I'm sorry, this caused a miss, and then we brought the data from the memory and we placed it here. Okay, so in this index, now we have data, right? And we need to save the tag for future comparison. Okay, and this is the memory here, this is the data. Now next, we look at address 26. Again, 11010, this is the location. This location did not have data, so we had a miss. We brought the data from the memory, we updated the valid, and we save the tag for future comparison. Okay, so you can see the dynamics now. Bring the data, when in case of a miss, we bring the data, we update the valid bit, and we save the tag for the data or for the block that I saved. Okay, and then what I have is address 22. There is data, and I'm comparing. I'm sorry. There is the address 22. We go to this set. There is data. Okay, and the tag matches the tag. So this is a hit. Okay, and now I can read the data to the CPU. Similarly, 26. This is the index. So I go to this set right here. Okay, and the tag 11 is the same as the tag. So I have data, number one, tag matches, number two, then this is a hit. So you can see now that to have a hit, I have to have first the valid bit equals yes, which means equals 1, which means there is a data, and tag must match. Okay, if the tag mismatch, I will have a miss. Okay, so so here the tag matches this tag, so I have a hit, and then I can read the data in the cache and send it to the CPU. Now notice here I have address address 16. This is 000. There was no data here. Okay, there was no data, so I brought the data from the memory, save it here, and then I save the tag here. Okay, and then I change the no to yes. Now notice here in this memory. Okay, I believe this is same here, because the see if there is. Okay, so here we have this address 3, which is 00010. This is for this set. Again, the data was not here, so we brought the data, we updated the tag, we updated, I'm sorry, the valid bit, and we save the tag over here. Okay, so miss. Then I read the address 16 again. So I decode the address set 0. Okay, so let's look at this highlighter. So set 0. Okay, which is this one. Oh, the data is there, valid data. How about the tag? The tag matches. Okay, so this is a hit. Okay, so a hit means I have the valid bit equals 1 or yes, and the tag matches, the tag of the address matches the tag saved in the cache. Okay, so now here we want to make sure that we remember this location. Here I have a data which is saved with a tag 11. So we have an address here 18, and this is for set 2, so we have to set 2. But set 2, we need to look at the tag that was here was 11. So we compare. So there is a data. Yes, there is a data. Okay, the valid bit is yes. Well, how about the tag? We compare 10, and here there is 11 before the update 11. Now the mismatch between the tag saved in the cache and the tag in the address causes a miss. So what we do, we go to the memory, we bring this data address, we save it in the cache, the valid bit is yes, and we save the tag, which is 10. Observe in the previous slide it was 11 here. Okay, now we have changed it to 10. Okay, so the miss here is caused by tag mismatch. Okay, all right. So basically, whenever we need to have a hit, what do we need to do? First, when I access, I take the index, I go and access the This is indirect mapping. This is indirect mapping because my map. So I pull the valid bit, then I have to check as well the tag in the instruction matches the tag that is saved. So condition number one, valid bit has to be 1. Second, the matching has to be okay. Then I will conclude I have a hit. And once I have a hit, I pull the data and send it to the CPU. Okay, good. Now, here he uses the more exercises in finding the tag bits and index bits and the block offset. I think we have addressed this quite a bit. You can leave this for as an example for you. Now, so we talked about the direct addressing, and we talked about uh, the fully associative, and we talked about in-way. So what's the difference between them? So first of all, the fully associative allow a given block to go anywhere in the memory, as we explained earlier. Uh, However, whenever I need to find some block in the cache, I need to do a search for the entire cache. This complicates the design. So I need a comparator per every set, every block. On the other hand, the in-way or the k-way, each set contains n entries. Okay, so we looked at example, I believe we looked at two ways. So every set in our previous example has 2 blocks, and the block number determines which the block number determines which set. So basically, I can take the index value and go to the appropriate set. So we need to search, once I go to appropriate set, right, I need to search all the blocks within a set. Okay, so all the given a set. So we need n comparator. So this is less complex than fully associative. Fully associative, they have good hit rate, but they are complex. Direct map, they have simpler design, but they have low hit rate. So somehow the in-way comes in an in-between solution, and provides for me a middle solution or a trade-off between complexity and hit rate. Okay, and here is here's an example of a direct map. You can see we have 8 blocks. Every block is a set, right? So we have 8 sets. Where if you have a two-way set associative, so this is a set. So whenever you want if your block maps to set 0, you have to search 2 blocks. But in the fully associative cache, if you have a block, then you have to search all these tags. So these are the tags here. Okay, so you have on the extreme, the direct, you search 1 tag in that set. On the fully associative, you have to search the entire tags in the cache. Well, for the in-way associative, k-way, you search k tags. Okay, right. Here's the organization of one-way set, which is the direct map. Okay, so you can see this is a set, all the way. So every set has 1 block. But two-way here, an example, you have here 2 blocks per set, 2 blocks per set, 2 blocks per set, 2 blocks per set. Okay, because this is two-way. Okay, and the 2 refers to number of blocks per set. Okay, now, oops, sorry. Now, how about 4-way? Well, this is a 4-way. Notice number of sets is decreasing here. We're having 8 sets, here 4 sets, and here 2 sets. But in every set, I have 4 blocks. This is set 0, and this is set 1. Okay, let's decrease number of set and like just 1 set here, set 0, and this is the fully associative, in fact, where the entire, all the blocks are in one set. That's the fully, so this is the direct, this is the fully associative, and these are the k-way. The one thing here you can say that the direct mapping is one-way set associative, and the fully associative is eight-way, where eight is the number of blocks in the cache in this example.